So I'm going to talk about performance tuning. A lot of this was talked about earlier, but my colleagues did a good job. Um, I'm going to my talk's going to be best practices, mainly focusing on the parallel performance. Some of the talks beforehand were really addressing the serial, except Jordan's talk kind of addressed some parallel performance, but I'll kind of try to reinforce what Jordan was saying with some concrete examples. On Monday it was mentioned that some colleagues don't really want to change if they're using 1.8. It works well for them, that they don't want to move on to a newer release of HDF5. So we have run past benchmarks for using HDF5. So this is one example where this is just creates a very large number of data sets, and it's the right time that we gather for all the earlier versions of HDF5. So from 1.6 all the way up to the newest one we just developed. And you can see that, yes, at certain versions, especially around 110, around the 112, it does not perform as well. But currently, with the current 114 and onward, we're really matching some of the performance of the earlier versions, namely 1.8. Another benchmark we have is CGNS, which I mentioned earlier, is the CFD standard. And this is just testing the make test that it has in serial. So this is the time it takes. We start with 1.8 and went all the way up to 114. Again, we see a little bump here. Earlier versions 110 and 112. But the 112, 114 versions are pretty much similar to what you see in earlier versions of later versions of 1.8. Of course, the earlier versions of 1.8 are really perform really well. In terms of parallel, the latest one I have is just scaling with CGNS again on Summit. So this is just using one of their benchmark cases and then running different versions of HDF5. So I have here 1.8, 110, and 112, and running on a different number of processors. So the different colors is the completion time. And typically for the parallel versions, we don't see as dramatic as effect of versions as we did for this serial version. So this just kind of gives you an idea of, yes, you can move on to the newest HDF5 version, hopefully get similar performances that you've been getting for the older versions. So some best practices affecting parallel performance. A lot of issues that we come across is whether you should create all your data sets or not, your groups, data sets, data types, all that stuff in a collective mode, or just do it on a single process, and just so you would open a file in a single process, create all your data structure, and then close the file, and then reopen in parallel and just write all the raw data in parallel. So you can do some performance. So here I have the time versus the number of ranks. And here, the blue is you create all those objects collectively. The red is you create all those objects with one process, close it, and then reopen it. And so you can see this is a little bit of performance. As you increase the number of ranks, you can see it's basically, of course, if you just do one process, it's basically just constant. You can get some performance degradation if you do that all collective as you increase the number of ranks. As you mentioned before, it's for datasets I/O. It's always better if you do parallel to do the largest I/O request possible. And parallel file systems really don't like small writes. It really hurts performance. So you can try to reorganize your writes and your data so that you are writing the largest amount of data as you can per I/O step. And of course, as it was mentioned, you can do data effect version. It's usually best to avoid it. And it's best to avoid data space conversion to get the best performance. Some of these can also create, for example, data type conversion can break collective operations. And if that happens, you can always check to see that you actually did the collective or independent operation as you expect by just two calls. You can do H5P get MPI actual IO. That tells you what actually, even though you said that wanted to collective, it might have bumped back to independent. And then if you want to know why, there's another call that will tell you why that was chosen by the library to actually do. In terms of storage type, as was mentioned, you can use continuous data storage. Is maybe your best option if you don't have to worry about extending your data sets or using compression. Of course, if you are extending it or using filters and compressions, you have to use chunk data sets. Another great option, and this is kind of overlooked a lot by users, is you can really use a compact storage. And that has advantage, and you can use it for small data sets. It has disadvantage, though, that you can't do like a hyperslab selection. You have to read the whole compact storage all at once. So it has a little limitation compared to a regular data set. But it becomes part of the internal metadata. So instead of having to write, for example, small data sets here and there, it will be written at the time that the metadata is written. So it's a way to avoid for these small data sets, these small writes. And as I said, it goes back to trying to write as large as data as you can on a parallel file system. And of course, to avoid data duplication, it's always best, for example, if you have a grid and it doesn't change through time steps, instead of rewriting that grid over and over, just use a link. That helps avoid writing unnecessary data. And you can also use virtual data sets we haven't really touched about in any of these talks, but this is another option to help try to eliminate duplicate data that you might have to write. Some scaling optimizations. So this is a CGNS benchmark that we had done before. And so the red was the original performance we were getting. So this is scaling up. This is the time versus the number of ranks. And you can see as the number of ranks for this particular benchmark, it went into days, which is basically unusable. We did introduce a new feature, well, it was new at the time, that instead of, if you're doing a H5S all, basically says you're reading all the ranks are reading the same data space. So instead of having all the ranks actually doing that operation, we have an optimization that if HDF5 detects that all the ranks are reading the same data, then it will just have one rank read the data and then broadcast it out to the others. And that's the green curve. So you can see that helped. That went from days to logs, so the days, the hours. And then we also have an option in CGNS that you can do implemented compact storage instead. And that really helped performance. And then he compared it to just doing a file per process, which is the blue curve here. And basically, the compact storage basically goes with the same scale as you do an MPI broadcast. So other strong, I guess I don't want to beat that horse. I always advise users to turn on collect metadata operations. If you can, I haven't found a use case that it doesn't help performance. Almost always helps performance. So if you can, as mentioned, do it, turn it on. As Jordan mentioned, the never fill chunk, that's always good thing to have. I would Rob Latham always at A&L always says, why is this still not the default on the newer systems? And I mean, the reason for it is because people are depending on that to be not never. So it'll become quite a shock when people heard, but we might have to have a discussion to have it to be the default in future versions. Just one where that comes up is if you create, as I mentioned, if you create your data set, your structure on one rank, in serial, it has different allocation times when you create those data sets. So in serial, it doesn't allocate the data until you actually write the data. Whereas if you read it now, so you create a data set with one rank, close a file, then you're going to reopen that data set in parallel. Well, parallel says, oh, I haven't allocated this yet. I'm going to have to allocate it. And when it allocates it, and you have this fill time to set true, then it's going to not only allocate it when you open that data set, it's also going to fill all those values. So this is where we came up with that idea. Unless you really need the fill time, to always just do never. So this is just an overview of performance tuning. So in parallel, it's a multi-tier problem. Of course, you have the HDF5 where you can tune it. And as mentioned, you can tune it with the cache chunks, whether you're using independent or collective. And then you can also tune under that layer, since the MPIO driver uses MPIO, of course. You can also tune at the MPIO layer. Then you have the parallel file system, which you can also tune by using set and stripe factor and stripe size. So all this is when you're doing it on a parallel file system, all this comes into play. So it makes it a much more complicated case, especially compared to the serial case. And one example, as we've mentioned in the past talks, is that the set alignment can have a pretty big impact. So this is the one test case that we had. We were running on Summit, which uses GPFS, and we were just monitoring the performance. So this is just alternating between independent and collective. And what we see, this is the write bandwidth, so gigabytes per second. So we switched from not aligning the data to aligning the data, and so it started off just here, and then when we turned on and actually aligned the data, it shot up on the bandwidth performance tremendously. It made almost 100 times better. So that was just changing one parameter on a GPFS file system. We don't see this type of dramatic as it's not as dramatic on Lustre as it is as we saw in GPFS. So it's always good to set the alignment if you can. Usually, that can increase your file size. That's also important too. So here I just monitored versus the number of processors, the percentage increase of the file size just due to setting that alignment. In this case, it's kind of the minimalist because this was just a contiguous data set. So it would just have one offset. If it wasn't aligned, it wouldn't be a big deal. Now, if you have chunk data sets, it could blow up your file size quite a bit. If you have to align it and the chunks don't align with that, it has to do a lot of padding. Then you can end up with a very large file size that just has basically blanks. So it's kind of a give and take whether you should set that or not. It depends on what you're doing for your data sets. So let's go back to just a fundamental, simple problem that people sometimes have. So you have a 2D array, and you want to write that over time. So of course you have that 2D array spread over D processors. You're looping over your time steps, and you're writing each array, whether you're scaling it up with the size of the grid, or you're keeping it constants. A lot of the questions when you first started with HDF5, well, how do I arrange this data? What's the best way to organize this data in the file itself? So some questions you might ask are, do I want to create 2D arrays, 3D arrays, 4D data sets? Do I know my extents unknown? Do I need to do compression? How are these dimensions ordered? How do I want to organize this in groups? Another thing to consider is what the order is the data written. Is it going to be read in the same way or differently? Is your read performance just as important as your write performance? And how the best do the storage layout? As mentioned, we need to give you a new chunk. I want to do compact storage. And of course, is the data compressible? And then what file system am I using? Am I going to do it on an object store? Is it Lustre or GPFS? And then finally, a lot of the questions is, well, what's better? Should I do always collective or always independent MPIO? So a lot of these is handled through the H5P interface. And of course, H5P mentioned it's very complex with the interface. But it doesn't necessarily mean it's difficult to use, it's just very complex. And depending on what your goal is, you might have you have to use more complexity than needed. So, for example, if your goal is to have a self-describing, share-friendly that is conforming to some kind of standard. So, for example, if you're using NetCDF or CGNS, their goal is maybe not necessarily as fast as possible, but they also want to be able to conform to the standards. On machine where you have different visualization packages, they know that this category of data set is corresponding to a certain quantity they standardized. That's important to them. Now, if you just want the fastest I/O possible, you don't really care if you're going to share the data, and you don't care if that's interpretable by other people. then yes, you can just do, for example, if you're doing checkpointing, just want to minimize the metadata you might generate, but that just creates maybe one group, maybe no groups, and just write one big either data set that's multidimensional, but you just want to do the largest write possible. So it depends on what your goal is for the final data. As was mentioned a lot, the H5P list is large. It's over 180 APIs. And basically it's used for the most part, it's the in-flight HDF5 behavior. So it's necessarily from the memory, how it gets back to disks, and some of the behavior that it performs to do that. And if you look at the combination of those, of course, it's ASP. How do you test all those combinations? So we've tried to, and one other thing is that, a lot of the APIs, people just set the H5P default and not really understanding that, yes, it's probably going to write the file, but it's going to write it in the most efficient and performant way. Maybe not. So it's always good to investigate why I'm using the H5P default. And maybe it's better in some cases to use H5P to try to optimize performance. So we've tried to have different ways. We try to investigate, and we came up with a program that kind of investigates different scenarios, different performance tuning techniques that you might come across. So this program basically cycles through, let me just go to the next one. It cycles through a parameter space. So it goes through, and so along this array, along the circle, you have different parameters that get changed. And so it will investigate along all the radius, or the radial of the circumference of this circle, and basically at each ray will do a different parameter set. So it starts off at the bottom, what the kind of data set rank you're using, and I'll discuss that in the next couple slides. What the slowest dimension is, changing what the slowest dimension is, that's the next outer ray. The storage layout, whether you're doing chunks or contiguous data sets, whether you initialize that fill value we talked about earlier, whether you're doing alignment, that tests that, what your metadata sizes are, and what version of the lower library version we mentioned also before, and then what kind of MPI operation you're using, whether you're using independent and collective. So for each ray, it will switch on and off those parameters. So going back to the first one, when you have an IO pattern model, for example, if you've got a step-based system, so you have a time step, you have, for in this case, 5 variables, and the dimension's 3 by 4. Well, you have an option of instead of writing each variable at a time, to combine those into a higher order array here. And then you also have the option to combine the time steps also now this is you're writing all of you've combined those into one big write of a big 4-dimensional array. The other option, of course, is you have you split your data according to variables, and then for each variable you write the time at each time step you write the data. You can also then collapse that as well by combining those time steps into another dimensional array, or you can again combine those and then have again one big 4-dimensional array with the leading index being the number of variables. That's what we mean by testing out different combinations of the parameter space. So now I've kind of flattened out those arrays. So these are the arrays. So starting with so the blue, that was, you chose to do the 2, 3, or 4, which I talked about in the previous 2 slides. Whether you're doing time step, this is, you have the contiguous or chunks, you have the fill value, yes or no, whether you're doing alignment. The metadata for this case, I just used the same, so that's not being tested. Whether you're using the earliest or the latest version of the HDF5 library, and whether you're doing independent or collective. So here I've then ordered so this is the graph below it, for each of those combinations is the average time that took. So you can see that if you were to choose This is on Summit, and then did weak scaling. So the best here, so this is the fastest time here, used this combination, which was the largest 4-rank array. It was chunk data set, had no fill values. The default used the default alignment, and it did independent I/O. So for this case scenario, this performed the best. So this is a log scale. So this is very performant. Now, if you were unfortunate and choose your data to be this one, then that would be bad for you. So it can affect the way you lay this out in some of the properties you choose can affect your performance by quite a bit. You can kind of, there is some efforts, of course, to minimize that effect. And one of the ways that was introduced was the log baseball. Basically, if you have, for example, you have your variable 1, variable 2 split out over, for example, these 3 ranks. You can have, by default, when you write these out in HDF5, you can have it have the 1 rank will write its P0 data, and then it will skip what rank 1 and 2 will write, and then it will write the next array position. It will write its data again with the P0. That's what that P0 write. So it has this kind of, it will write its 0 and then it'll skip and write its 1 and skip. Now what the log baseball does is it tries to make that more contiguous. So the processor 0 will write its data right next to processor 2, and then it kind of makes it so it's more contiguous in the file. What this ends up being, it's still an HDF5 file. It just rearranges the data in a more, I guess, a better way for the file system to handle. If you now look at that same graph, you can see that now I haven't reordered it, so I just ordered the order that the parameter space is. So the yellow curve here is the peaks and valleys. So these perform very well. This perform very poorly. So this is just using a native vol. Now, if you use the log vol, it kind of evens out the peaks and valleys of that and gets better performance independent of what you really chose in your parameter space. So that's another option to try to mitigate. The one issue though is to understand the data, you'll have to load that vol back up so it can interpret the data as you expect. Of course, another feature is to use async I/O. This can kind of where you just try to overlap the I/O with the computation. It has an advantage that you choose not the best option, but it's really not as important because you're kind of hiding that I/O over computation. So even if you don't have the fastest I/O parameters, you still might get very good performance because you're kind of overlapping the computation with the I/O. So that's another option to try to speed up your I/O, just use async I/O. And this is an example of using async. So this is on Summit, and the blue is with async as the number of ranks increases. So this is the gigabytes per second, and you can see that without async, it's very slow bandwidth compared to with async, very good. So that's another option. And of course, I won't mention it again, but subfiling is another way to get really good performance if you want to go over that route. And that's all that I have for mine. Questions?
Okay, let me get the microphone. I think it works. We do have one question.
Can you expand a little bit on when alignment works and when doesn't? For example, a user blocks compression.
It will always work, whether it gets good performance or it blows up, as I said, your file size, then it depends on how you have it laid out. But for compression, if you have alignment, I don't know, Jordan might have to answer that, because I think kind of alluded to it in his talk, that if you have compression, it's not as clear. Jordan, you want to?
Yeah, the main thing, Scott, is that even if you have compression, you always want to try and align your data chunks to a stripe boundary. It's just that depending on how the compression does, you might be able to fit multiple chunks in a single stripe boundary. You might, if the compression ends up increasing the size of the chunk, you may end up splitting across a stripe boundary. But in general, you'll pretty much always get at least equal performance if you can align everything to a stripe boundary. It's just the main trade-off is, of course, the file size may get bigger, even significantly bigger.
That answers.
Yes, so if I understood correctly, Jordan, then the library will take care of, if the compression ratio is high, it will take care of putting multiple chunks in the same.
Correct. It should, even if your chunk gets compressed, it should still align it to the stripe boundary. It's just that typically chunk sizes are often smaller than the stripe size, so you can often fit multiple chunks within a single stripe, which is generally pretty good for performance. But depending on how the compression works, you may end up splitting a chunk across the stripe boundary. It kind of depends there, but at least a few of the chunks would end up aligned well.
Wait, you're saying that if the chunk shrinks by a factor more than 2, that it would put the second chunk behind the first chunk within the same stripe?
It should generally align within the same stripe, but it's going to depend on your chunk size versus the stripe size, whether or not it's going to go across the stripe boundary.
Well, I thought it would just always align each chunk to the start of whatever your alignment is, right?
Again, it'll depend on the settings you have for the set alignment. It has a threshold value, right. And yeah, it depending on what your final chunk size ends up as will determine whether or not it gets aligned or not. And so that's why I say it complicates things a little bit in my talk, because typically when you're picking a threshold value for your alignment, you'll go with whatever your chunk size is. So 1 megabyte, for example. But if the compression changes that around, some chunks may not get aligned how you're expecting.
So, Jordan, just to repeat what you are saying, when you set an alignment, then the first chunk will be aligned on the stripe boundary or page boundary. And then depending on the parameter, you may fit more chunks into the stripe, or you may end up in a situation when chunk is split between 2 stripes, which you didn't intend, no one intended to do, right?
I think the answer is that if the chunk is over the size threshold, then it always starts on the whatever the alignment boundary is, right? Which is probably your stripe size.
Right, but if it's less, then it will be with the first chunk or whatever.
Well, with the first chunk, I mean, I don't think there's anything special about the first chunk. So
right. No, but it may fit in the same stripe, right?
It may just happen to fit. Like if the first chunk, you're right, is over the threshold and it goes on the stripe boundary, the second chunk is under the threshold, it might go behind the first chunk, but it might also go before it in some other stripe.
Right. Right.
It's just not aligned at all.
So bottom line, some chunks may not be aligned on the boundary.
If you set the threshold high enough.
Right.
If you every chunk to be aligned, then set the threshold lower.
Mm-hmm. Thank you.
Thanks, Elena. Thanks,
I was
Scott.
going to add one thing to that.
Oh, okay, make it quick.
Elena, you were mentioning earlier, yesterday, day before, wanting to have all the chunks that you create sequentially aligned in the file. And if you use alignment, there will be gaps between them. That idea would need some more refinement.
Right. And I was also talking about non-compressed chunks in the for the first optimization.